frame ground is really what you use to shield this cable. And under most circumstances, it'll be connected to the frame on one end and the shield, and not even connected on the other, so that you don't get ground loops. Sometimes it helps to have it connected on both ends, and sometimes it doesn't. That's one way to help to reduce interference getting into that cable, like RF. Now this is the side that your terminal is on, your computer, or that cheap $10 terminal that you buy from the SwapFest, from the Denver Radio Club's SwapFest. And remember that sometimes it wants to see certain leads high. Like it wants to see this signal clear to send coming back from this data communications equipment or your TNC. If you don't have that lead connected, there's an easy way for you to take care of it, and that's from data terminal ready, which is a high signal, and you can just put it back. Sometimes he also wants to see data carrier detect. So if you're typing on your TNC and you don't get anything, or you're typing on your terminal and you're not getting anything back from the TNC, one of the things that you may want to do is start connecting pin 20 over to pin 8, over to pin 6, which is data set ready, and also over to pin 5, which is clear to send. So you might want to bring all or any of those high positive voltage in order to get your terminal to start responding to the data coming in. Okay, the leads that you want to be concerned with on your terminal are pin 5, which is clear to send, pin 6, which is data set ready, and pin 8, which is data carrier detect. Now if this were actually connected to a modem, those signals would have some significance. If you do run, one other thing too, and that's like the PK232, you cannot run all the leads through. If you run all the leads through, you'll lock up your TNC, because there are some conflicting leads that the PK232 uses for its printer port. So they have a special cable that splits out the printer information. So if you don't use that special cable, that special printer cable, just run signal ground, or send data, receive data, signal ground, which is pin 7, and you can also run pin 1. No, I just soon. I'll wind up playing with it. We talked about this being an electrical standard, and what the RS-232 standard does define are electrical voltages on the interface. And RS-232 says that you must be able to, if you are the originator of the signal, like data set ready, you must be able to drive this voltage when this terminal is connected to at least plus 5 volts and minus 5 volts, and not to exceed plus 15 or minus 15.
Is that always on the pin 5?
No, that's any of these that its appropriate thing sends. In other words, for the modem, it's pin 5, pin 6, pin 8, and pin 3. And conversely, from the terminal, those leads that the terminal would normally drive. So if you get on there with a voltmeter, now that's when you have a standard RS-232 terminator on the other end. If it's open, the voltages can go as high as 25 volts. Any questions about the RS-32? Yes?
One thing on that, you said that you have to have a high voltage on those three, at least those three, in order to begin transmitting data.
Maybe and maybe not.
My question was, are you referring to a continuously high voltage once you get started and then that stays on? You're talking about a space.
No.
Okay.
No, I'm talking about a positive voltage may be required on 8, 6, and 5 of the terminal. You need to look and see. You know, you need to. In other words, that's one of the things to try if it doesn't work. Is to and one place you can find positive voltage usually is on pin 20. This indicates that the power is on and the terminal is in an on state and ready to go. So you can take and feed those back. And most of the time it works where you can feed this voltage back to 8 and 6 and 5 all at the same time. You can also sometimes find a positive voltage on pin 4, which is request to send. So you need to kind of pick and choose. You need to kind of find out where you need to be. Okay, next slide. Okay, we talked last week about the 3 types of frames. The unnumbered frame, and the unnumbered frames are used to control the link, set up a link, disconnect a link, report protocol errors, define status, and allow roundtables where you can have unnumbered information frames that everybody can get. Only problem with that is you need to also set yourself into some sort of a condition where you can receive everything. The supervisory frames, this is how we keep the link going. This is how we can control the frame flow from one end to the other. We confirm receipt of iframes. This is one way, is through the use of supervisory. Another way is also through information frames. This standard is really rooted in a standard that IBM developed a long time ago called SDLC, Synchronous Data Link Control. Using a lot of the same sorts of things, and IBM, in their infinite wisdom, didn't like the way that things were going in terms of data communication flow back and forth, because in order to acknowledge a frame, we had to stop transmission, we'd send a frame, and then we wait for you to acknowledge it. You know, did it get there okay? And if it did, then I'd send you another frame and you'd acknowledge it, and we would go back and forth like this. This allowed the capability of a bit-oriented protocol of being able to send more than one frame, keep a couple of balls in the air, and hopefully we'll get an acknowledgement back before we have to stop. Of course, we do that in a full duplex line. This is where we're talking about an asynchronous, where we are still going back and forth, but it still allows us to be able to send information in a bit-oriented fashion, so that we can send, we can acknowledge a frame by sending a frame of information. Okay, let's look at these unnumbered frames. Any questions? We're going to get into each of these types as we go along. Next slide. Okay, the unnumbered frames are, we said that these were for link setup and teardown and whatever. The SABM, which is a connect, if you will. When you issue a connect, a SABM goes out, set asynchronous balance mode. And asynchronous balance mode means, asynchronous means I'm going to transmit, wait for the line to be free, and then you're going to transmit. Or somebody else is going to transmit. depending on the timers. The disconnect, which is just that, it disconnects a connection. An unnumbered acknowledgement is what you send if you want to accept somebody's connection, you want to accept somebody's SABM. If you don't want to accept somebody's SABM, you send them a disconnect mode which says, I'm busy, or I can't accept your call, I can't accept what you are trying to send me. And if for some reason we've got a basic protocol violation with the frame you sent, I'm going to send you a frame reject, FRMR. Along with this, I'm also going to send you some information about what I thought was wrong with it. Too many characters in the information frame. Means you got everything okay. It means that the frame check sequence on the end of the packet was okay, but there was something wrong in the way it was developed. Probably won't see that too often. And then the unnumbered information, which is used for roundtables. Any questions? Yes?
Those designators are actually what appear on the screen, correct?
Yes. Yeah, you'll see something exactly like that, close to it. Oh, one other item here. The UA is not only used just to acknowledge a SABM, it's also used to acknowledge a disconnect. We'll look at each one of these in a lot more detail through the night. We're going to look at some typical sessions and how these are used. Okay? Yes?
The balanced mode in that term comes from the fact, I guess, that you're going to permit them to transmit as soon as you finish transmitting? Or
I think it has to do with some more basic things on how you handle, in balance mode, everybody's the same status. There are some modes where you give up control by where once you've gained control, you have control over the link until you give up that control through the use of P-bits. Balance mode means, yeah, if I can send, I can gain control of the link. I can send unsolicited if I need to. Where an unbalanced mode means you're going to have one person in charge of that link until he gives up charge of it. You see a lot of that in real full-blown X.25. You'll see non-balanced. But in here, you can take charge if the circuit's idle. If you need to. I mean, if your TNC needs a response for something, then you can come up and transmit the appropriate supervisory controls. Okay, let's look at the next one. Any other questions on the previous slide? Okay, let's look at the supervisory frames. We're going to look at these in some detail, and trying to get you know, what is this different from FRMR, and this is different. It gives some different information. But we have a receiver ready, which means just that. The receiver's ready. We can use it to say receiver ready, or we can say receiver ready. In other words, it can be a command or a response, depending on just exactly when it's sent. Receiver not ready can also be, is one of those that can be either way. Can be a response, which it usually is, indicates that your station is there, it's functioning, but for some reason I just can't receive right now. Got your frame okay, got your request, but I'm not ready to receive, like a full buffer. And then the rejecting, we'll look at this in some detail later on to see how that's used. And a reject, what that means is that we received some frames a little bit out of order. And that's only because we had a data error or something like that happen on the line, happen on the circuit. Any questions about that? Okay? Oh,
Why, what would be the difference between using a UA and an RR? In other words, if somebody sends a SABM, would that be the same as saying receiver ready question?
no. The protocol says that when I send a SABM to you, your correct response is an unnumbered acknowledgement. Yeah. Simple as that. The protocol says that is the appropriate response to a SABM.
So that's
Or,
setting things up.
pardon me?
That's setting things up. That's
Yes.
saying we're going to communicate.
That's right. So I say, may I communicate with you? And your two responses are, only two allowable responses are, three responses are, UA, which says yeah, DM, which says no, I'm busy, or I can't accept your request, or FRMR, I don't like that SABM at all. You got something wrong in it. You got information in there where it's not supposed to be, and it's just supposed to be a simple frame, and now you got information, and you got stuff in there you shouldn't. So those are the three responses that you can send to me, and that's what the protocol says. A protocol is just a set of rules. So what we're trying to do here is we're trying to learn the set of rules and a lot of the ins and outs, because these are the rules that that are governed by everything, and by looking at the rules and being able to decipher the rules and see where the rules are not necessarily broken, but by analyzing the protocol, by analyzing these frames going back and forth, it can tell you a lot about what's happening or problems that are happening on the service. Now remember, we're sharing a circuit. We're time sharing a circuit with a whole bunch of people. That's one good thing about Packet. It's difficult to time share like on a repeater, except you go around, you go around robin. But you get some people that don't want to time share so easily, so well. But it allows Bill and I to be able to talk about the inane stuff that Bill and I talk about, as well as the inane stuff that the rest of you talk about, and we can all do it at the same time. And I don't even care what you guys are talking about. Bill and I are, concerned with what we're talking about. It's awfully good communications, Liz. Any other questions?
Only good thing about it.
Well, there's a couple of other things good about it. Hopefully we'll get into those too.
Okay, you.
Any other questions? Okay. Bill checked this one out. He went back to the book and he looked to see that 14 to 21 octets has been changed in the new book. Okay. And it reflects the fact that you can have 8 digis. The thing that's important here is that for each one of the digis you have to have 7 bytes of information. 7 octets. 7 8-bit units. We talked about the flag, which is a unique sequence coming down the line. That 0 followed by 6 1 bits followed by a 0 is a unique pattern. Are you saying, well, why couldn't we have, like in the address, you know, I'm not sure exactly what that decodes to, but why couldn't we have that in the address or have that as part of the ASCII data? As a matter of fact, this is the only time that you'll see 6 1 bits in a row. That's a special indicator. Remember now that while we're receiving this, we don't know where this end is. The only way we know where the end is where we get these 6 1 bits in a row again. Then we back up and we say, well, the 2 octets just before that is the frame check sequence. And then I have to quickly do a calculation of the frame that I just received by doing the algorithm that's necessary in order to generate this frame check sequence, which is really kind of a complicated process because it's a multiplication of the bits and and it's a remainder, a 16-bit remainder, 2 octets, if you will. But all of this now is done on a chip. I mean, that's done automatically on a chip. You just feed it the data and it pops out this here, and it's done almost instantly. Takes microseconds to do. In the old days, they used to do that with a complicated assembly language program. Yes?
Well, when you transmit a program, binary, is this all different?
No?
I mean, you could have that bit combination in a binary sequence of bytes.
Certainly. Yeah, you could even have this in ASCII.
So how does
What this is, yeah, this is a tilde. That's what this character is in ASCII. It's a tilde. Before it processes any bits, though, it will look and it will see if it's not a flag. Like let's say we're in the address field, and let's say part of the address field is one of those tildes, which has got 6 1 bits in a row. What he does is he sends 5 of those bits and inserts a 0, and then continues to send and keep looking to see if there are 6 1 bits in a row. If there is, he sends 5 of them, puts a 0 in, and keeps looking until he finds 6 more in a row, sends 5, puts a 0 in, and then continues sending, sends the next one. And it's called 0 insertion. So what do you have to do on the receive side? Okay, you got 5 1 bits coming down the road. If you get the 6th one, you know it's a flag. If you don't get the 6th one, you know that it's been a 0 that's been inserted. And again, this is all done on a chip. It's done automatically. So that's how you can send binary data. That's how you can send, like let's say you had, in the information frame, let's say you want to send 8 1 bits in a row. You send 5, insert a 0, send the next 3. And on the receive side, you take them all out. You take all those inserted zeros out. And the way you know is, if you get 5 1 bits in a row, and the next one's a 0, you know that was an inserted 0, you throw it away. Yes?
I've wondered about that now with that 0 stuffing. Are you actually in ASCII protocol when you're doing that? I guess the question is,
No,
that's not ASCII really, right?
No, that's kind of like a preprocessor that, remember now, we within the machine, like let's say we're typing away and we're sending a message to somebody. This is the information that we're typing in. And when you hit the return key, or this is now as full as it can get, he packages this. And what he does is he puts in the address, puts in the control, puts in the frame check sequence to match all of this, and then he sends a flag, and then he begins sending bits, doing the 0 insertion, followed by a flag at the end. There's a number of ways of doing it. You can set all this up and then go in with a little program to look and see where you got 6 1-bits in a row and move things around so that you can insert. So there's any number of ways of doing it. But usually on the transmitter chip itself that generates the flag, it will also does the 0 insertion. It's all part of a standard chipset. The same chipset that does the frame check sequence also is part of that 0 insertion, 0 deletion. Yes?
A probably unimportant question.
No question is
The
unimportant.
next frame, do you have a flag, information, flag, or is it?
This can be the ending of this one and the beginning of the next one. Yeah.
So you don't need 2 flags?
No. No, as long as we got this delimiter, this can tell us this is the ending of this one, this is the beginning of this one. Yeah, you don't have to have a flag at the beginning and the end. This could be the ending flag of the previous frame, if you're sending your frames one right after the other. It's all part of IBM's scheme to make data communications flow better.
So this Marvel chip they've got only does the 0 insertion and deletion after it's seen a flag. That must somehow set the thing internally to start 0 inserting.
0 insertion is part of the transmission scheme. In other words, the rules say, the protocol says that I can't send 6 1-bits in a row unless I want it to be this flag. Okay? So it's part of the transmission scheme that when I transmit, I won't, that's part of the rules. Rule number 1 is that I won't send 6 1-bits in a row unless I want it to be a flag. And in order to not send 6 1-bits in a row, I send 5, insert a 0, and then continue sending 1-bits.
So actually that's more akin to being buried in somewhere in the instructions in the controller.
Yeah, that's it takes care of all of that for you. This is just a sidelight so that you know what some of the complexities are of that TNC. It's not a trivial task, not a trivial machine. It's a real computer. Just as another sidelight, if you send 5 1-bits in a row and the next one happens to be a 0, you still insert a 0.
It will do that.
Yes. Yeah, it does that whether you want it to or not. Can't turn it off, can't turn it on, it's there.
So it actually lengthens the information field
By a few bits, yeah. Depending on how many patterns you have of 5 bits or more. Yeah, so the frame, yeah, if you're in the habit of sending frames with lots of 1-bits in a row, your frames are going to be a little longer.
PID stands for what?
That is the packet ID bit. This is generally not used by a TNC. These are generally used by nodes to do. Remember we talked about nodes that had the capability of being able to do automatic routing. In order to do automatic routing, I need to send my routing table from me to all the people that can hear me so they know who I can hear. So that if somebody on their node wants to get a hold of somebody that I hear over here, that node over there needs to know how to get from here to there. And what he'd do is he'd send that information, and if you've ever had your TNC turned on, and you get all this racket but don't see anything happening, maybe all you see is a receiver ready, and you wonder, boy, that's the longest receiver ready I've ever heard in my life. It could be one of two things. Could be TCP/IP, which is another protocol, high-level protocol, or it could be nodes sending out their node list. One of the two things. But then your TNC generally is not set up to monitor when that PID bit is set. Anything I'm forgetting here, Bill? Probably adding a lot more than was there, right? Any other questions? You're making this easy for me by asking these questions. Probably something that I should have prefaced before. There are no inappropriate or stupid questions, because a question that you ask is probably a question that a guy like myself, I'm not very vocal in a class usually, and I sit there and I just wait for things to go along, and if nobody asks the question, it never gets answered as far as I'm concerned. But the people that ask the questions really, if there's some confusion in your mind, there's probably confusion elsewhere. So.
You said packet ID bits, but would
Yeah.
it take more than just a bit to identify a...
What do you know about PID, Bill?
It's basically just one bit. And anytime your TNC is sending information, it's at a 0. If a node that you're connected to hears that frame and sees the bit at 0, he ignores it. If you have a TNC where you have firmware set up in it to act as a node, like DNet and NetROM that we're going to get into here very soon, or as Joe mentioned, you have two nodes that want to exchange routing information, they set that one bit to a 1. And when the node brings that in, he says, uh-oh, that is information for me. This is housekeeping, network housekeeping information. So therefore, I have to look at it and do something with it. So your TNC will always have that at a 0 to indicate that it's what's called level 2. It's you talking to a node or talking to another ham. But if it's a 1, then it's the network device talking to another network device. That's how they distinguish the information fields. What's user information and what's network information. That answer the question? I'm not sure I heard the whole.
Yeah, that was.
But it's just a single bit to designate who the information is for.
Yeah, the question was, is that really one bit? And the answer is yes. Yes.
Yeah, maybe I'm too hung up on the 0 insertion, but I wonder if you could tell me how it knows not to stuff a 0 in a flag.
Oh, because he knows, as part of the rules, he knows that he has to start out with this flag.
I can see at the start. It's at the end I've got a problem.
Okay, after he's run all of these bits down here, he knows he has to have a trailing flag. It's just part of the rules. And this is generally part of the signaling that's outside of the 0 insertion, so to speak.
So it can kind of recognizes those trailing bits somehow, and then it knows that means there's a flag coming, I guess, right? Well,
Yeah, how would it distinguish those 6 ones from 6 ones someplace else before?
But remember now, we're gonna insert a 0 before we get to 6 1 bits.
Yeah, I realize that, but how does it, how does it know when to stop inserting zeros? I mean, how does it know that it's at the flag and say, okay, now it's all right to send 6 ones?
When we set up this frame to begin with, it's a finite width. And when we run out of information, when we've run out of the frame check sequence, we know we have to send a flag. When we're out of information, we got to send this flag. And the hardware knows to do that. Yes?
Is the information that's coming in processed to get rid of the 6 ones before the frame is built? That would answer his question.
Actually, remember now, this is coming in this direction. So this is the first thing that you see. This triggers us to begin zero deletion. When we're receiving this frame, as soon as we see this, we know that the very next thing is going to be the address. And on the next slide, we'll be able to look and see what tells us the end of the address. And then we're going to get this one byte of control information. Now we're going to get the information frame. Then we're going to have the 2 bytes of this. Actually, we don't know where the end is until we've counted 6 1-bits in a row. And then we can come back and we can look to see where that frame check sequence is. After we've taken it entirely into our buffer. Yes, Woody?
So if you send out 2 packets, you have your first flag, and then you send out your packet.
Yes.
Your trailing flag, and then immediately you'll have another flag for your next packet. If you send out 2 packets side by side, do you have 2 flags side by side? In other words, you have start and end.
You can.
Start and end.
You can, but you don't have to. This can be the ending flag and the beginning all in one flag.
Okay,
You don't.
Flag, 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 flag.
Yeah.
You don't get pairs of them.
No, you don't. No, you don't have to.
Packets. Okay.
An interesting sidelight here is if you should happen to get 7 1-bits in a row, that's an abort signal. That says throw away everything that you received. That's the way that you send an abort. Yes?
When you type the word abort on a cam, is that what it does?
No.
It sends out, that's an actual command on the cam.
That's a command on the cam
7 ones out
to disconnect. That, in other words, if you don't want to disconnect, if you want him to send the disconnect to you and you UA him, you say abort. Right? No, that's by.
On a cam, if you type a
Oh, okay. That's a control. That's a control to. The question is the abort the same thing when you type abort on a cam? And an abort, if I'm remembering, is a command to kill the connect that you just requested.
yeah, whatever you've asked it to
Yeah,
do.
and that's just a control sequence for the cam. Yes. Yes.
You say that you can have a flag, or you don't have to have a flag. And I'm kind of thinking back to Joe's question of determining when the zeros are inserted and when they're not. So who determines? Is it your computer that determines if you have 2 flags?
Well, remember now, if you you could have one or many in here, depending on exactly how your terminal is set. As a matter of fact, you probably have quite a few out here, because when you bring your TNC up and you begin transmitting, you need to have some period of time for the receiving station to be able to get in time with you. It's not quite like the asynchronous signal that we looked at before, where you have a start bit that gets you started. You need to look at these transitions coming down the line and shift your clock so that you're looking in the middle of each one of those transitions. Takes a little bit of time. So you have a parameter that says TX delay. What that is how long am I going to delay before I begin sending my frame? And usually what's sent are flags, because it sends a lot of transitions. That's how we derive timing on the receive side, is by looking at several of these. And we derive the timing internally according to when we see these transitions on the line. So there could be more. How does it know? Anytime it sees 6 1-bits in a row, it knows that that was a flag.
because sometimes you're inserting the zeros, and sometimes you're not.
Yeah, the only time you're not is when it's a flag.
When it's a flag.
Yeah.
Okay. And
So you know, your hardware knows when it's going to send a flag.
Okay, I guess that's my
That's
question.
in the
Yeah.
TNC, not in the terminal, right?
Oh, yeah, that's in the TNC. That's all done for you.
Okay.
Yeah, you don't have to worry about it while you're typing. That's all done automatically.
Would my TNC always send 2 flags or always send 1 flag in terms of between the frames? Would it be consistent?
Probably would be. Yeah, it's written in the software. And how many you have on the beginning, of course, is a matter of how long your TX delay is. Sometimes you hear people bring up carrier, and you hear kind of a constant pattern for a long time before you get the data. What they have is a very long TX delay, probably much longer than they need. And those are some of the things that we're going to talk about. So you're good citizens on the packet, because remember, you're sharing it, time sharing it with a whole bunch of other people. You don't want to hog the frequency. Yes.
I think Bill mentioned a parameter called max frame, which you could set. Did that have anything to do with how many of these you would transmit at a time?
Max frame. Pack length?
Max frame.
Max frame,
Pack length?
4 frames before technology.
Oh, okay.
Pack length is,
Yeah, we're going to look at max frame in some depth tonight. We're going to look and see what that, what significance that has. We're going to look at it in terms of, we're going to look at it on a nice clean channel. What it means if you've got, where you can send 7 frames without being acknowledged. We're going to look at it when, like on an HF system, where you send a lot of them. Something to remember here. We'll hold on there until we get to the next slide. That is something I want to point out in the next slide, I believe. Yes.
Just curious, how does the TNC know, say on a multi-connect, when the address field is through
Okay.
and that octet is coming in?
Perfect timing. Are there any other questions? Let's go to the next slide. He knows that we're at the end. He knows that we're at the end of the address by having a 1-bit in the most significant place. None of these other bytes has a 1-bit in the most significant place. Only this last one, and that's the SSID of the last repeater, or if all we have is a destination and source and no repeater, it would be the SSID of the source would have that 1-bit set in the most significant bit. Remember that ASCII is really a 7-bit code. You talked about parity. In this case, we're using 0 parity in our address field, and we're using an indicator in this last SSID to indicate that that's the end of the address field. So that tells us when we've come to the end. Yes, Woody?
I was just wondering, did you define least significant and most significant bit for people that have never been exposed to it before?
No, not really. The least significant bit is the first one sent online, but they're gathered into 8-bit increments and stored as 8-bit bytes after the zeros have been deleted, and they're put into storage. Okay? Least significant, most significant only has to do with when it was received online. So this is the first bit that would come down the line in the address field. Now we said we could have a destination, a source, and up to 8 repeated by. Now remember, every repeater that you put in here, you've got another 7 bytes of information. So that makes the frame longer. And also, because it's longer, means that it's possibly more susceptible to error. This part of it, by the way, is unique and is not part of the SDLC standard that IBM designed. There is an address byte in SDLC, but it's only 1 byte. And it can take on the range of from a binary 0, all zeros, to binary where all are 1s, or 256 different addresses. And in some cases, you can actually use that to address 256 different stations on a circuit, and was used that way. In our case, because we need to talk about call letters and SSIDs, we need to have it 7 bytes long for each address. Okay? Any other questions? Following the address field is this control field that we talked about, which is the information and whatever. We're going to look at a breakout of that control field next. Is it appropriate to break right around 8? It's a good place to stop and get started on brand new information. So we've been just reviewing.
On packet, the other day, Woody was sitting on 10 meters, I was sitting on 20 meters. We were both running our stations remotely, so we couldn't change the dial. We're not supposed to put that in there. So we couldn't run home and change the dials.
We're on lunch, of course.
And we're about a mile apart physically. So we set up a link from 10 meters to California, San Mateo, then crossed over to 145.01, went down to San Jose, to Mount Umunhum, south of San Jose, crossed over to 144.96, went down to the east side of San Jose, connected to K6MGM, another gateway, came out on 20 meters and connected to me. So we sat there a mile apart talking to each other over a circuit that was about 2,000 miles or so long. Had about 4 frequencies involved.
It took about 45 seconds, right?
In fact,
What was this that Joe mentioned about being a gentleman or don't mess up?
gentlemen. So anyway, that's just another little story of some of the things you can do on packet.
I'm just curious. I'm gonna, you guys are in the lead. Most of us, I'm sure, have never even begun to.
Well, in about 2 weeks, we're going to start talking about how to do all this stuff.
Well, yeah, but I mean, how long? When you sent something, I once linked with a friend down in Dallas, but it took me a long time.
On 2 meters?
Yeah.
Okay,
I went through
that's
at
a
least
different story.
8, repeaters. But how long did it take? Like when you wanted to say something, how long till he heard it? I'm just curious.
Oh, what was it? About anywhere from 20 seconds to...
About 45 seconds from
Yeah.
the time I hit the return to the time you saw it.
Now, I experimented one time with a guy in California. I went all the way on 2 meters to California, San Jose. And that was 12 of these nodes all linked together. And then we were talking. See, you always talk on voice to compare what you're doing on packet, right? So we were talking on 10 meters. We had sporadic E going. And I'd say, okay, Lou, I'm hitting my carriage return, time it. I'd hit it. And then we'd time it. And it took anywhere from 20 seconds to a minute and a half. It just depended on how much traffic was going on and retries, da-da-da-da. It was pretty fast.
Well, he did. He was on both of them on the telephone to see when it started.
Well, we had a case the other night. CB, who wanted to be in this class, had to go to work in Las Vegas. And he has a TNC set up there in his apartment. So I went all the way on 2 meters and connected to him, to his mailbox, and I started leaving him mail, and all of a sudden the link went away. And then, Les, you'll enjoy this. I give up about 10 o'clock at night. Phone rings. It's CB from Las Vegas. Well, I wanted to let you know what happened. He says, I was trying to figure out how to get you out of my mailbox so I could talk to you, and I hung up the entire system and locked it up. And I thought, well, that's like to know about this. You always got to get on the phone and compare what went wrong on packet. Keith?
NX0M, Gus?
Right here.
KC8JP?
Right here.
I'd,
What do you want the fire protector on?
there we go. Okay, we're going to get into a new one now. We're going to start talking about some new information and not the old. And we talked about the flag, we talked about zero insertion, we talked about the address, how it could be variable length. The fact that the most significant bit is set to 1 to indicate when we've come to the end of the address field. And now we're going to talk about the control field, which is 1 8-bit byte. And boy, can it contain a lot of information. And this is really kind of the guts and the wherewithal to the protocol that IBM created. And it's not so important to remember whether or not this first bit is a 1 or a 0 or those sorts of things, but we'll cover it just real quickly. In this first octet, Bill, these are laid out most significant, least significant? No, it's the other way, right? This is the least significant bit? Do you remember?
I don't have my glasses on, I can't see it. You're right, Joe.
This is least significant?
Yeah.
It's been a while since I've looked at these bits. I looked at this slide and I thought I had it pretty well down. Okay, so this is the first one that's transmitted online down here, and these out here are the ones that are transmitted last online. At any rate, if when you're sending an information frame, if this contains information, you indicate that by sending an information frame. As part of the information frame, the middle bit, kind of the middle, almost the middle bit, since there's no middle in an even number, right? It's something called a P or F bit, and that whether it's a P bit or an F bit is just a matter of what you call it. But a P bit would be used for a command of sorts. You'll notice that an iframe is a command. So here's some information. And whether or not I set this bit or not is determine whether or not I require you to respond to me or not. Supervisory frames have the first 4 bits in a unique pattern to determine what type of supervisory they are, as well as unnumbered. So there's a unique set of 4 bits, but the first bit is always going to be a 1. The only one that has the first bit as a 0 is the information frame. On in,
P and F stand for?
poll and final.
What's that?
Poll, P-O-L-L, and final. We'll look to see just what significance that has as we get along. Usually when you set the poll bit, you're demanding something, or you're relinquishing control back to the other side in a non-balanced mode. So the supervisory frames also have something called numbering. There are 3 bits set aside for numbering. In an information frame, we can number both ways. We can number the frame that we're sending. Remember, Bill talked about numbering the envelopes when you send them? This is our numbering scheme for numbering the envelopes as we send them. We got 3 bits. What's the maximum number you can use? 0 through 7, 8, right? So you can number up to 8 frames. So what do? You just roll it over. After you send frame number 7, you send 0 next, and so on. But this protocol allows you to be able to send up to 7 of them without getting an acknowledgement. So you can number 7, and then you have to stop at that point and get an acknowledgement. So this has to do with MaxFrame. How many are we going to allow here to send? We'll look at this further on down the line in some detail. What do we got? Somebody connecting to us?
Joe, I left the monitor on.
Oh, okay. The receiving count tells the other end about where we think his send is. It's a way of being able to say or acknowledge frames, is by incrementing the receive. You'll notice that the supervisory frames also have the capability of being able to send to the other end a number indicating where he thinks his send should be, which envelope he's expecting next. And that's what this stands for. The NS stands for next send, and NR stands for next received. We looked in the unnumbered here. We see some unique bit patterns of the first 4 bits for the SABM, the DM, the disconnect, the UA, and the FRMR. And you'll notice that they don't have a count, hence unnumbered. Hence we call it unnumbered. And you'll notice that these are either commands or responses depending on what you're doing. A SABM is a command. It'll always be used, I want to connect to you. And you need to come up with one of these responses. Remember I said that the only response you could have was a disconnect mode, a UA, or an FRMR. If my SABM wasn't configured properly, you might send me an FRMR. You would send me a UA if you wanted to accept my connect, and you'd send me a DM if you didn't want to accept my connect. So those are the proper responses to the command SABM. When somebody sends you a disconnect, you've only got one choice. Well, you got 2 choices, just like I said. You can go unnumbered, which acknowledges the fact that you want to disconnect, or you send an FRMR if there's something drastically wrong with the protocol of the frame. A SABM does not have information. If your TNC for some reason went nuts and started putting information in here, you might send an FRMR saying, that's completely wrong. Not supposed to have information in there. I don't know what that is. question.
Okay, so I know what next send is here, next receive. I got lost on the O and P. What should I call those?
P and F,
Yeah, well, I know that stands for either P.
poll or final.
But what does the P up on top stand for there?
Here, poll.
Just poll?
Yeah. In other words, a command, we call that bit the P bit.
Okay.
And that's why, because a receiver ready can be either a command or a response.
And then the, to your left,
This
0
one here?
Or O?
Well, is that, no, that's a 0, indicating the first bit
Okay.
is going to be a 0 on an information frame. That's what makes it unique.
Oh, okay, I see. We're in the information. I get it.
Yeah,
all.
see, this is an information frame. So this frame would have information. As it turns out, so would this unnumbered, I'm sorry. We don't have the UI on here. Any other question? Yes.
You may have said this, P is a 0 and F's a 1 or vice versa?
No. If the question is a P is a 1 and a F is a 0, whatever. If you want to say in your information frame, if you want to say that this is a poll, and we'll look at this as we go on some of these other frames. If this is going to be your last frame, you're going to elicit a response by setting the poll bit to 1. So you're saying, I'm going to poll you, I'm going to send this, and now I want you to respond to this because this is all I've got for you for right now. Or I've hit max frame. So here we go, and I'm going to issue a command saying I want you to respond. So that's how I'll do it. If I'm sending 3 frames in a row, the first 2 frames usually will contain a 0. Although they could contain a 1. As long as I still got the circuit, you can't send, as long as you hear me. But normally, the first 2 frames are going to contain 0s, and the last one that you send is going to contain a 1, which says, I positively want you to respond. I want you to tell me how you got my frames. Did you get them? You know. Did you get all of them? Did you miss one? You know, so on and so forth. And you can tell me that information by responding with a receiver ready. You could also respond, because you can tell me what you received, you could send me an iframe back if you had one sitting there waiting. That's part of IBM's scheme to make the data communications channel a little bit more efficient. In the good old days, you had to send an acknowledgement, which was like half a dozen characters. Now you can send it in 3 bits, tagged along an information frame going back the other way. There was a question where? Right here.
This term you used, max frame, means what?
Means how many of these are we going to send before we wait for a response? What's the maximum number of frames that we're going to send before we get a response? Now, we know what the maximum allowable in the protocol is. We can only have 7 before we roll this counter over, before we repeat the number. So we can, the protocol allows us to go up to 7. But if the circuit conditions don't indicate that we should go 7 unacknowledged, then you want to tell your TNC to only send 2, or maybe even 1. Wait for a response after each one. All part of learning all the ins and outs so that you're a good citizen and so that you can get your data communication through, so you can get your packets through. On VHF, you set your packet size pretty large, and you set max frames a lot of times to 7. Because the channel is very good, less chance of an error. And for general communications, that works pretty well. What about on a busy channel when you got a lot of people vying for the circuit? Maybe you ought to run fewer frames.
30.
Run 30 what?
So when you get it, you can keep it.
TCP/IP does that for us. So you be a good citizen. Plus the fact that, because not everybody can hear everybody, I may not hear the guy over here that's interfering with me to the same station I'm trying to send to. So he doesn't hear me and I don't hear him, but the guy that I'm trying to send to hears him just fine. So I come up and I transmit, and I try and transmit 7 frames. Right in the middle of what I'm transmitting, he transmits because he doesn't hear me. He thinks he's being a good citizen, which he probably is. But he interferes with my packet. So maybe I should just send a couple and hope I got them through. So it's a matter of that sort of thing. Protocol does allow you to go up to 7, but that doesn't mean you have to always use it. Information frame can have 128 bytes. But there are conditions, especially on HF, where you don't want to send that big of a packet, because the odds of it getting clobbered on HF are pretty bad, because it's going so slow. It's only going 300 bits per second. When the connection is made, when a SABM is sent, part of the things that are done when you do a set asynchronous balance mode is to take these counters and set them to 0, so that we start out from scratch. So we're always going to start out with our counters sitting at 0. Any other questions about this? I'm going to ask you to now let's go to this next frame. We can come back to this one, and we probably will if there's a need for it. So kind of keep your finger in that slot, because we may be coming back to this. Let's go to the next slide. And this kind of sets the stage here for most of what we are going to talk about. After an initial connection up here that you don't see, a SABM was sent and a UA was responded to, so we've got a connection. We said, you want to talk via packet, and the other side said sure. Okay, so we got the circuit up. On one side, they sent connect, W60AV. And on the other side, W60AV said, on his screen, it said connected to and who was calling him. Let's say it was me, KE0QA. So on my machine, I said connect W60AV, which sent out a SABM, and on Bill's screen, it would say connected to KE0QA, and his machine would send a UA back to my machine. Now, on my machine, it would say connected to W60AV. And now we're in the converse mode. Means automatically the TNC would put us into a mode where we can start typing to each other. So I'm a real fast typist, being a computer programmer that I am. So I start typing away, and the very first packet that I send out is going to have a a packet number of 0. In computers, nowhere else do you start out with 0. You know, I mean, this is always finger number 1, 2, 3, 4, and so on. In computers, this would be finger 0. 1, 2, 3, 4. And I always thought I had 5 fingers, or 4 fingers and a thumb. But in computerese, we always start out with 0. So anyway, we're going to send an iframe, and the number that we're going to put on that very first one is 0. And let's say that because I'm typing fast, I'm going to follow it right next with another iframe, and you'll notice that I changed the NS count, the send count. And this is a legend of the way they are. The first number is the send count, and the next number is the receive count. Because remember, an iframe contains both. Contains not only the number of the frame that we're sending, but it contains the number that we expect next, hence next receive. So we're still expecting him to send us 0. So we send 0 and we send 1. Because I'm typing away, I send 2. Now at this point I either hit the return, or my fingers are falling off because I type so fast, and I stop. or we've set max frame to 3. It says DTE must receive a response before I3 can be sent. So apparently max frame is sent to is set to 3. So we can only send 3 frames without an acknowledgement. So once we send these 3 frames, this side, because Bill is a little slower on the trigger than I am, he didn't have anything typed to send back to me, so he's going to send back a receiver ready. And on his receiver ready, he's going to say, I got your 0, I got your 1, I got your 2, and I'm expecting number 3 from you next. That's how I acknowledge that I received 0, 1, 2, 0, 1, and 2, is by saying, I'm expecting you to send me 3 next. That's the same thing as saying, I got your 1, your 0, 1, and 2. Nowhere else but IBM counts from 0 and says, I want, or that I'm expecting this from you next. There's probably a good reason. I haven't figured it out yet.
They only have 1 digit there instead of 2 when you get to 10.
What's that?
Well, so you can go from 1 to 10 with only 1 digit each, instead of having 2 digits when you get to 10.
Yeah, there's only 3 bits, so you can only go to 7 anyway. So, yeah, I know what you mean. I know precisely what you mean. Yes.
Does that mean you got them error-free?
Oh, yes. Absolutely. If one of these had been clobbered, this would look different. And we'll look at that situation. We'll look at that precise situation. Yeah, when you send that you're expecting number 3 next, that does mean that you got all the frames from the last time that you sent a next received. And you see as you go along that that this indicates, yeah, I got them all. All of them up to this point, I got them all in my buffer. And I printed them on the screen. Yes?
When I set max frame in my TNC, is that the number of frames I will send?
The maximum number?
Or
That's the maximum number that you will send.
so if the other person has a different max number, he may send 6 back to me
Oh, yeah.
before I give him a 3
Yeah. But now remember, that's maximum. You have to be a pretty quick typer. You have to be lightning fast. Or if you're a bulletin board or something like that where you have a lot of information coming out, then you get into the, into the max frames. Usually keyboard to keyboard, it isn't so much a problem. Unless you get on a real bad circuit and you send one frame, then you send another frame. Well, this frame never got there, and it got clobbered, or one thing or another. Or the circuit's real busy. You may back these things up. But under normal circumstances, this would happen on a bulletin board sort of situation, at least on VHF packet. That's a maximum, not a minimum. Minimum is 1. Yes?
Yeah, up at the top, we were talking about 2 stations. Now it looks like a terminal talking to modem, or I mean,
Yeah.
see, why do we have that?
Why is that, Bill? These are actually 2 different stations talking to each other.
So it's really not a DTE and a DC?
No, not really.
Okay.
Oh,
Right, Bill?
I forgot to take those off when I photographed them.
Okay. Bill's problem. Go ahead.
okay, on this DTE has no information to send, so forth.
Yes.
The arrow's pointing from DCE over to DTE.
Well, look at this. Look at this as being KE0QA station, NW60AV station. Remember now, Bill's a little slower on the keyboard, so he didn't have anything to send back. So on this iframe, I probably sent him a P-bit, which says, I want you to send a response to me. Okay? So he didn't have a frame ready to go, so he had to respond with something, and a receiver ready, he not only had to respond, but he should respond with a numbered frame so that he can tell me which frame he expects me to send next, so he can acknowledge, where he's at.
So that's W60AL you're talking about.
Yeah, W60AV, that's that guy back there.
W60AV, I mean,
Yeah.
has no information to send.
Yeah. Now, if he did, this looks a little different. He would send an iframe. He would send the 0 iframe, and he would put in his NR count, he'd put 3, and in his send count, he'd put 0, because he's sending frame 0, and at the same time, he could be acknowledging
Okay,
that frame.
What I'm getting at is, shouldn't that say DCE has no information to send?
Yeah.
That's what I was trying to get at.
Oh, okay. Yeah, we should probably change that.
That was in the book, by the way. These came out of a manual for X.25, and they talk DTE, DCE terms, and I was hurriedly throwing these together for the first and only class that we were going to run back in those days.
Yeah.
So we're going to redo all these.
Okay.
We'll probably put them on the Mac and do it up nice. Yes.
I just, on those, as those frames are coming through, you're never gonna have a situation where one would get hit, and you would get, or 0 would get hit, and you would receive 1 or 2. You're never.
Yeah, we're going to talk about that. Yeah, you betcha. Any and all of that's possible, right? Any of those frames could get clobbered. Absolutely. Something to remember, when a frame gets clobbered, the frame check sequence is not going to match the information that we received. And if the frame check sequence doesn't match, we throw the frame away. Even if it's got our call on the front. We throw it away because we don't even know if the call is correct. We don't know what information is clobbered. Yes, where was it?
Effectively, that receiver ready 3 is the acknowledgement.
Yes.
We refer to the act.
Yes. Remember now, on a receiver ready, and we can go back to that chart, but on a receiver ready, he gives us the NR count, the next received count, and what he puts in that count is a binary 3 in those 3 bits. So he puts a binary 3 in there to indicate that we're expecting number 3 next, and that's saying, yeah, I got 0, 1, and 2, and I'm expecting 3 next. Yes.
Now, with that, with the acknowledgement, how long would it be then before you send another receiver ready if Bill is still sworn he's supposed to be? And excuse me, Bill, I got agitation a little bit. But
His comments were so boring, I fell asleep at the keyboard.
well, that's one way to put it. And you will send out another receiver ready at some point. Won't you?
You mean if I didn't get this?
If Bill didn't respond to you with receiver ready, if he did not come back with information 3,
Oh, yeah. Or
at some point you would tell him again, wake up.
oh yeah, absolutely. Let's say it got clobbered. What do I do then? I didn't receive it. the frame check sequence on this didn't come through, so for all intents and purposes, Bill didn't send it. At least I didn't receive it. So what do I do here? I got to do something, because I sent him 3 frames. I'd like to know if you got them. Come on, tell me. Because I said, tell me when I sent this iframe, tell me, I'm done sending now, tell me what you got. And we'll cover those scenarios of what happens when the data channel doesn't work too well. Right now we're looking, what we're trying to get used to right now is how we go back and forth and how we handle this numbering scheme. It's a little bit screwy to think of this numbering scheme because you're really talking about next sent, next receive. So I'm just trying to get you used to looking at these flow diagrams, and we're going to be working off of these as we go along. But they will tell you something, and once you learn how to use these flow diagrams, they really do tell you how the protocol should work. And when you're looking at the screen and you've got it set on monitor and you're looking at these packets going back and forth, and you see a situation, you can equate it back to these flows. So, Bill responded with a receiver ready, and we'll assume that I got it. I had another packet ready to go, so I sent iframe number 3. If this was the last frame to be sent, I'd set the pull bit, and I'd expect a response out of Bill, and so on. So this continues on for our entire conversation. Let's look at the whole lash up with a little different thing on the next frame. We're going to get a lot of practice looking at these. Here's the entire connection, by golly. Looks like Bill doesn't have an awful lot to say, right? That's all right. So here I am, and DTE means KE0QA. We can make that change in our book, and that's Bill over there. And so, as I usually do, I connect to Bill, and I send a connect W60AV, which sends a SABM out, and Bill is always there, so he always responds with that UA. He's got his users set to about 30, I guess, all the time with that Packet Gold program he's got, so he might be having conversations with people all over the world. That's probably why he's not responding here. He's already talking to K6MGM out on the West Coast, and somebody in a bulletin board, some international bulletin board gateway, whatever. Anyway, so he sends me the UA, and I start sending packets. And again, the SABM says we're going to set all of our counters to 0. So when I start sending, I say I'm going to send number 0, and I'm expecting 0 from you because I haven't received anything from you yet. Then I'm going to send number 1. And that's all I got to send. Couldn't type quite so quick. My fingers are so tired already. And on this packet here, I set the P bit to 1, saying I want a response. Bill says, by golly, I got your 0 and 1, because I'm expecting you to send number 2 next. So he acknowledges that. And I, like a good citizen, wait to make sure that the channel is clear, wait my turn, a random amount of time. Then I send information frame number 2, the one that he expected, and information frame number 3. Catching my second wind here, I send information frame number 4, send third straight packet in a row, and on this one I send the P bit set to 1, saying I want a response. And Bill sends a receiver ready 5 to me, saying that he expects number 5 next. He got 2, 3, and 4.
When the frame gets to 7, does it recycle back to 0?
Yes.
So that it knows 7, the next one will be 0.
Yes. Yeah, if I send frame, and I'm almost certain we're going to look at this. If I send, huh?
We will look at that.
Yeah. If I send frame 7, the next frame I'm going to send is 0. So if I send 7 and 0, he would respond to me with, if he got them both, with a receiver ready 2, saying I expect 2 next. I'm sorry, receiver ready 1. I expect 1 next, because I sent 7 and 0. Yeah. The same thing here, if I sent 0 and stopped, Bill would respond with, receiver ready 1. I'm expecting 1 next. I got you 0, now send me 1. That's what I'm expecting next. Yes?
You're being a good citizen and you're waiting. You said a random amount of time.
Yeah, that's all part of the algorithm of the TNC. What parameter is that, Bill? The random wait persist?
Wait for response before you...
No. Wait for the circuit to be idle.
Oh, okay. There's several. One is called persist and slot time. It's a very complicated thing. And each TNC that has these bases that time on a random number so that you don't have everybody waiting for 2 seconds and all coming up at the same time. Okay.
When I say I'm being a good citizen, the TNC is being the good citizen. I can set that lower if I want to be a bad citizen, but if you want to be a good citizen, you set it for the recommended, or actually all you need to do is look at the default in the TNC, and that's the number that's generally recommended, usually. You don't want to touch it. Just leave it the way it is. And then everybody's got the same, everybody runs that same algorithm, and so sometimes you'll be a little bit behind, but you're being a good citizen. You're letting other people timeshare the circuit. Yes?
Now, in this case, you said the P-bit was set to 4. I don't know if you ever said it. That's a command, I guess, you give from your terminal somehow, or is that...
No. The TNC handles that for you. He knows when you start sending these frames, if you've got consecutive frames to send, usually. If he doesn't, let's say he set the P-bit to 1 here, and while he was sending this frame out, he realized he had another frame to send. He just continues sending as long as he doesn't reach his max frame, and set this to a 1. Remember, when you got the circuit, you got it. And you continue, you can continue sending. So it's no big shakes if you put an extra 1 bit in there.
So, I'm trying to think now in terms of what that means from the computer talking to the TNC. It means that maybe the number of bits, or the number of frames coming up might be more than the TNC thinks it is, and all of a sudden it gets more dumped on it than the computer.
Could be.
But it doesn't matter, I guess, from what you're saying.
Yeah, it doesn't really matter. The TNC is going to handle putting in these P-bits. I mean, that's part of the protocol that the TNC handles for you. Yeah, you don't need to say, well, I'm going to set the P-bit to 1, and it does that automatically for you. We want you to know about this, however. You can look at these channels, and we'll look at some of these broken out also in the back there.
If your max frame was set to 3, it'll set the P-bit after 3 frames. If you had a carriage return, would that set it after less frames if you type less data?
Yeah, probably. Yeah. Yeah, if that's the only frame you got. In other words, if you typed and you hit the carriage return, that automatically sets up the frame. Puts the flag in the front, works on the address, puts the address in, the control, the frame check sequence at the end, does all the 0 insertion for you and all of that kind of stuff, and then ships that frame out. And if that's the only one that the TNC knows about now, he probably would set the P-bit to 1. If all of a sudden he had another one to go, and if he can get it done quick enough, maybe he'd send the second one right after it with the P-bit set to 1. In this protocol, it's not so essential. In unbalanced mode, that's a completely different story. But in this protocol, in balanced mode, it's not too important. Yes.
This is probably a little bit off the subject, but this makes me wonder on, I'm not really in packet yet, but I've noticed when I see people working it, sometimes when they type a long string, in other words, they get a word wrap or carrier return on their screen. It looks to me like you get the same thing at the other end. In other words, that person at the other end sees that carrier return, or is that really just a matter strictly of the hardware, the computer hardware? In other words, is a TNC sending a return without having the operator hit a return?
No.
Okay.
If you keep typing on the keyboard and you go past the 80 characters, there's some terminals that will automatically wrap that to the next line as you're typing. So there's two things that can cause a frame to be generated. Generally, one is if you hit the return key, that says I'm done with that frame. However long it is, send it. If it's less than the maximum length that I've set for a frame, send it anyway. If you continue typing, as soon as you get to the maximum length, pack length, which is a parameter, which sets the amount of numbers of characters that can be in the iframe, then it's going to packetize that, even if you don't hit a return. Okay, well, does that answer your question?
Yeah, so pack length is what the TNC stock.
Yeah. I don't think there's anything in the protocol that says you can't have more than one carriage return in a packet. But normally when you're keyboarding, a carriage return will cause a packet to be generated. That's only good sense, because usually when you're typing and you're done typing, you know, if it's a short message, you want it to go as soon as you get done typing, you hit a carriage return and that will cause a packet to be sent. If you didn't happen to be done typing and you continue typing, no big deal, you know. So you sent a packet that was a little bit shorter than it could be. Question back here.
Is this where my retry comes in?
No, this is something different.
Keeps requesting
We'll look at those.
ready.
Yeah, we'll look at those situations where you request a response and it doesn't come, or you issue a request to connect to somebody, you do a SABM to somebody, and you don't get the UA. You know, you wait a certain amount of time and you try it again. Wait a certain amount of time, try it again. How many times am I going to try? That's max tries. Okay, so you know there's, but that's something different. Question over here.
If you're TNC and it wraps, it sends that out. Does that mean that the default is set to about 80?
No. If I continue typing, goes out on the screen and wraps around to the beginning of the next line.
It sends that first line out.
No, it doesn't. If there's no carriage return in it, let's say you've got pack length set to 128 on a good, VHF circuit. So you got pack length set to 128. It will, as long as you keep typing and you don't enter a return, it'll go to the 128th character before it actually packetizes, and there's no carriage return in it.
But I'm asking you, if it does, as soon as you get to the wrap, it sends that first line out. Does that mean your parameter's been set down to 80?
Oh, 80, yes. Yes. Okay, I misunderstood your question. The question is, or the question was, if you find that your TNC is sending a packet, when you get to the 80th character, what does that mean? Well, it means the pack length is set to 80. So if you type 80 characters and you don't hit a return, if it sends a packet then, what that means is that pack length is set to 80. Nothing wrong with that either, except some terminals don't do automatic wrap. So they just sit there and bang away at the end of the line. Display characters at the end of the line. Liz?
Now think you at least answered part of what I was going to comment. Some of the terminals have a setting, it's a parameter, to where you get to the end as an automatic return.
Yeah.
And some of them do not have. I run into that problem.
Yep. So again, to be a good citizen. And when I'm mobile packeting, at least in the old days, I had a 40 column terminal, a TRS-80 100, one of the Radio Shack laptops. Great for mobile packet. But it's only 40 columns. It does automatic wrap, but when people start sending 80 column lines or 80 character lines, it eats up that screen pretty quick, and boy, you know.
Your wife
So-
like to drive when you run that thing?
Well, she used to run it, and I'd drive. I never get to read when I'm driving. I'm running this packet station. I don't know. Anyway. Yes.
Packlink. Does that include not only information, but the flags, the address,
No.
and all, or just the information?
Just the information. That's how many bytes of information you put in.
Then actually a packet is longer than that. All the time.
Oh, yes. Well, the packet's always longer than the information, certainly. Yeah. Yes.
Maybe I misunderstood. You say that information frame had maximum length of 128?
Yes.
Because you can set backland up to 255, 256,
Is that right?
on MFJ you can set it at 256.
The default is 128. A lot of them you can go longer than that. That's the
Oh, my. Really? Because X.25, see, I'm working in the world of real X.25, and most packet networks only allow 128. Because they want to charge you for every packet you send, so they want to make it smaller, right?
Well, this wraparound,
Like AT&T and some of them other.
this wraparound probably
The old ones will allow you to go beyond 128. Some of the original ones I know did.
Yeah, that's kind of a understanding, general understanding about packet length is. I didn't know you could go 256.
if you have a wraparound problem, can't you also set auto line feed and carriage return?
Some do, some don't.
Some do, some don't.
Yeah, depends on your TNC. Yeah.
Jim says you have it on the MFJ.
Set auto line feed and carriage return on.
I think
Okay.
the 232 has that too.
Yeah, I never use it. Yeah. As fast as I type, I still put in carriage returns. What's not so good about not being here next week is we need to, we're going to need to start kind of over on these diagrams again. So if you have an opportunity to look at these again and just get yourself familiar so we can kind of take off running 2 weeks from now, I really would appreciate it. Yes?
Yeah, you might start reading at about part 14 of those digital articles that you have, either in floppy or hard copy, because that goes over this. And actually, the diagrams in there are a little better than these. And it shows examples of I-frame, acknowledging an I-frame, the things that we didn't really show you. So if you want to read that over, that'll reinforce what Jim's covered. Those articles are basically following the class, so if you want to read ahead, then you'll be one up on it when you come in week after next.
Thank you very much for coming. You're really a good group. Really a great group.